In this video, I want to talk about the same quantities and the same ideas that we've been talking about, namely eigenvalues and eigenvectors, but in the case of 3 by 3 matrices. So 3 by 3 matrices. All the definitions are the same. It's just that the computations are one step higher. So because we have a 3 by 3 matrix. So what we're going to do is let's just compute this. And what I want to do is I want to look at I'm going to give you a matrix A. So let's say that A is the matrix. In this case, it's a 3 by 3 matrix. 0, 0, negative 2, 1, 2, 1, and 1, 0, 3. And what we're going to do is I want to find the eigenvalues and eigenspaces for A. Okay, so that's what we're after. So we're going to start by, there's no nice formula here. There's no nice formula for the characteristic equation in terms of the determinant and the trace and anything else. So nothing that useful is there for 3 by 3 matrices. Of course, there are some patterns, but it's easier in this case just to go through and do the processes one step at a time. So let's do this. So here's our matrix A. What we're going to do is we're going to compute the determinant of A minus lambda I. Here I is a 3 by 3 matrix. I'll probably stop writing the subscript here, but it's a 3 by 3 matrix, so I'll just write it in this case. And so this is going to be the determinant of A, 1, 2, 1, 1, 0, 3, minus lambda I. So this is going to be the identity times lambda. And if we compute this, this is the determinant of the matrix 0 minus lambda, 0, negative 2 minus 0, 1 minus 0, 2 minus lambda, 1 minus 0, 1 minus 0, 0 minus 0, 3 minus lambda. All right, and it looks like the easiest way to compute this determinant is via the second column. It doesn't really matter how we compute it, but it looks like that's the easiest. So we're going to get 2 minus lambda times the quantity, and if we cross off the middle row and middle column, we end up with this 2 by 2 submatrix, negative lambda, negative 2, 1, 3 minus lambda. So the determinant of that is going to be negative lambda times 3 minus lambda minus 1 times negative 2. And this is going to work out to be 2 minus lambda times the quantity, let's see, negative 3 lambda plus lambda squared plus 2. So this is 2 minus lambda times lambda squared minus 3 lambda plus 2. Lambda squared minus 3 lambda plus 2 happens to be lambda minus 2 times lambda minus 1. And so what I can do with the first quantity, 2 minus lambda, is factor a negative out of that, and then switch the order, lambda minus 2. And this works out to be negative quantity, lambda minus 2 squared, times lambda minus 1. That's our characteristic polynomial. Okay, so this is our characteristic polynomial, p of lambda. So, of course, if p of lambda is equal to 0, that means that lambda is going to be, our eigenvalues are going to be 2 and 1. And what I want to do then is compute the eigenspace for each of these. So I want to compute the eigenspace. So I want to compute the eigenspace E1. And this is going to be the null space of the vector A minus 1 lambda. Right, so this is really the same as looking at A minus 1I. And this is going to be, let's see, if lambda is 1, then A minus I is going to be minus 1, 0, negative 2, 1, 1, 1, and 1, 0, 2. And then we're going to augment that with the 0 matrix. We're going to augment that with the 0 matrix. We're going to solve it. it turns out that this is going to be, let's do this in 2 steps here. I can get the 1, 0, 2 up top. Let's make our bottom one a row of zeros. So what I did is I switched, however you want to think about that, I switched row 1 and row 3, and then I added row 1 to row 3 to cancel it out. And then I'm going to subtract row 1 from row 2. And so that's going to give us, that's going to lead us to, we're going to have 1, 0, 2. Row of zeros in the bottom. And then if I subtract row 1 from row 2, we're going to have 0. 1 minus 0 is 1. 1 minus 2 is -1. And so that means that our solutions, e sub 1, is going to be the set of all vectors. Let's see how to parameterize this. Let's let x3 be t. And then x2 is going to be t. And x1 will be -2t. Because remember, the way that I'm doing this, I think this is worth just remembering, because we've done so much this semester, is that this top equation means that 1x1 plus 0x2 plus 2x3 is 0. The second equation says that x2 minus x3 is 0. And so if x3 is t, then solving each of these for x1 and x2 respectively gives us that x1 is -2x3, x2 is x3, and therefore if x3 is t, that's how I get the other values for x1 and x2 here. Okay, so it looks like the eigenspace e sub 1 is going to be the space -2t, t, t, where t is a real number. In other words, this will be the span of the vector -2, 1, 1, or the span of any other non-zero multiple of that vector. I mean, I could, if I want, I could move the minus out of there. It really, this part is completely irrelevant, right? It could be, I could multiply that vector by 5 and it would still be the right thing. So anyway, so that's the eigenspace e sub 1. What we're going to do then is we're going to do the same thing for e sub 2. Remember that we only have 2 eigenvalues here. We only have 2 eigenvalues. We have lambda equals 1 and lambda equals 2. Notice that lambda equals 1 has multiplicity 1, because that's a hidden 1 exponent there. But this lambda, this eigenvalue, namely 2, has multiplicity 2. And so again, I know that these are the only 2 eigenvalues because we solved the equation, but if I add the multiplicities, 2 plus 1, I get 3, which makes sense because this is a 3rd degree polynomial in lambda. Our characteristic polynomial is a 3rd degree polynomial. So anyway, so our only other eigenvalue to check is e sub 2. And what we're going to do is, remember, we're trying to solve a minus lambda I times x equals 0. And that works out to be, if I take a minus lambda I, where lambda is 2, that's going to be -2, 0, -2, 1, 0, 1, and 1, 0, 1. So it turns out that this is going to be what we get when we take a minus lambda I and plug in lambda equals 2. And this is going to simplify to be 1, 0, 1, and everything else is zeros. And so now let's think about how to parameterize this. Of course, we can let x3 be t like usual, but there's no restrictions on x2, right? There's nothing that we're saying about x2. x2 can be whatever we want. x2 we'll call s. x1 we're going to call minus t, because the first equation says that x1 plus x3 is 0. The bottom 2 lines say x2 is anything. There's no restrictions at all on what we can say about x2. So x2 can be anything. And if we put those together, this is what we get. So this means that e sub 2 is going to be the set of vectors of the form -t, s, t, where s and t are allowed to be any arbitrary real number. Or you could think of this, if you want, as negative t, 0t, plus 0s0, where again s and t are allowed to be whatever real number we want. Or finally, I think it's best just to write this as the span of those two vectors, or any scaled version of those vectors, negative 1, 0, 1, and 0, 1, 0. Okay, so that's the eigenspace corresponding to the eigenvalue 2. Notice that this eigenspace E sub 2 is a two-dimensional space. That did not have to be the case, but it turned out that that was possible because 2 was an eigenvalue of multiplicity 2. So the dimension, I should just add that the dimension of E sub lambda is going to be less than or equal to the multiplicity of lambda, where the multiplicity is, again, the power that you have for x minus lambda in your, or for lambda minus whatever value in your characteristic polynomial. So the dimension of the eigenspace always is going to be less than or equal to the multiplicity of lambda.